In this video we're going to do some signal processing using data about the position of the International Space Station as an example. So the data we're going to use is coming from this web page here, spotthestation.nasa.gov, and we can download the file from these links here. So let's have a look at what the file is. We've got so here's the file iss.txt. And you can see there's a bunch of kind of header stuff at the beginning, and then we've got a bunch of data, lots of data rows down below. The header, okay, so header, the kind of key thing we actually want to pay attention to in the header is this little section here about events. So there's a comment, there's a GMT 117 reboost preliminary. This is when you fire some rockets to raise the orbit of the International Space Station by a little bit, which they have to do from time to time because there's a little bit of air resistance that causes the orbit to drop over time. And then there's another event where there's the SpaceX 30 was a spacecraft that was delivering supplies to the International Space Station. It undocks at a certain point, and then another spacecraft kind of relocates from one attachment point to the International Space Station to another. So we need so there's going to be these events are going to have some effect on the orbit of the International Space Station, so we have to sort of take account of that. Notice here that it specifies the time here. It's 0250 as the time for this first event, but it says 117. That 117, that means it's the 117th day of 2024. Which we've got. Turns out that's actually April 26th, and then April 30th is this day 121 here. So we're going to need to take account of that. But the main thing we want to pay attention to is this data down here. So in first thing here, we've got a specification of the time that we're looking at. So it's an ordinary date, 2024. It's April 19th here, or mostly April 19th. And then we've got about a couple of weeks worth of data. So it goes. If we scroll down far enough, it'll go past April 19th. And then we've got the time in 12:00, 12:04, etc. So it's normally increasing by 4 minutes from each measurement to the next, but not absolutely always. We're going to have to do a little bit of work to tidy up the data set to get rid of the anomalies where we don't. It's not a 4-minute gap between measurements. And then we've got kind of 6 numbers here. These are kind of X, Y, and Z coordinates of position, X, Y, and Z coordinates of velocity. We're actually going to discard the velocity and just deal with the position. I haven't actually worked out exactly what coordinate system they're using for these X, Y, and Z coordinates. You can take it as a kind of challenge to chase that up if you want. But for the moment, we'll just accept this X, Y, and Z coordinates with respect to some coordinate frame or other. Okay. So yeah, how are we going to read this file? So we're going to start, as usual, we're going to need to import some stuff. Okay, so we've imported matplotlib as usual, and numpy, and we're going to need datetime and also scipy. Okay, okay, so now we're going to import, we're going to read all the lines from the ISS file. Yes. Okay, so now we've read in the lines from this ISS file. So we've got lines now as a list of these lines, and Okay, so now we want to kind of parse this. Okay, so we just want to look at the data lines. The data lines are the ones that start with 2024, right? Okay, so if it doesn't start with 2024, then we'll just skip it. Okay. And then so then we're going to split the line. So if we just do split with no argument, then that'll just split it at the spaces. But we've got plenty of spaces here, so that's as good a way as any to split the thing up into fields. Okay, so actually let's just okay, so now we've just done the first line that has data in, and then we've stopped this. Okay, so here we've got all these strings here. Okay, so okay, so now we want to sort of get the stuff, get the data from here, and then we're going to do and record it. Okay, so we're going to do. So we're going to, we're just going to look at the x, y, and z coordinates which are here. So we're going to do that. Okay, so remember this string here is x0, so we want x1, x2, x3. Okay, but we want to convert these from strings into actual floating point numbers. So we just have to wrap it with float like this. Okay, so now now we're okay. So, but yeah, we've got the x, y, and z things, but we actually wanted to know the time as well. Okay, so okay, so the time is kind of like this. So what are we going to do with that? Okay, so I've got a string like this. How do we convert this into some kind of time that we can actually deal with? So we imported this datetime library here, and so the way to parse a string like that is to use datetime.datetime.structime. Okay, so that's strip time, that's string parse time or something. Okay, okay, and then so we're going to feed in this s, but then we also kind of need to tell it, what's the kind of format. Okay, so so we firstly put in a kind of %y dash. So %y, capital Y, refers to a 4-digit year, so that's kind of matching this to 2024, and then the dash kind of matches the literal dash there. And then we do %capital M, %little m, that's going to be for a 2-digit month, and then %d for a 2-digit day. Okay, and then we've got this character capital T here, this is the literal capital T, so we put that in there. And then and then you have %h for the hours, %m for the minutes, and %s for the seconds. But then, okay, so let's try that. Okay, so it doesn't match the format. That's because we've got this kind of .000 here, which we need to kind of get rid of. So Right. So we do colon -4. That'll get rid of the. I'm not sure if we need colon -4 or colon -5. Okay, so now, okay, that's okay. We see we're getting an error message here. That's because we messed up slightly. We should have colons instead of dashes here. Okay, so now that's worked. Okay, so by doing the colon -4, we get rid of the last 4 characters here, the sort of extra 0 digits we don't care about, and then it matches this format that we've written here, and we get a datetime object. Okay, but this is some kind of fancy object, and we don't really want a fancy object. We want a number. So we can do .timestamp. That gives us a number. This is a standard computer representation of dates and times. This is a number of seconds from the beginning of 1970. Okay, so so that gives us a number. Okay, but there's no seconds from the beginning of 1970. It would be better actually if we had the number of seconds from the beginning of our data set. So what we're going to do here is we're going to put in okay, we're going to do t start is none, and now we're going to do we're going to do t is this basically this thing that we just got here, except that instead of s, yeah, so here we're going to do x of 0, so that's going to be the first part of the line that we just did. Okay, so that's the time. Okay, and then now if we're so for the first record, we want to set t start to be equal to that time. So if t start is none, that means we haven't worked out the start time yet. Then okay, so then the start time is this t. Okay, okay, so in the first loop through this first pass through this loop, we're going to set t start to be equal to the relevant time. And now we're going to do t as t minus t start. So now we've got the number of seconds from the beginning of the data set. And now we're going to put that t into our data set. Okay, so now our first element thing is we've got the t is 0 and so on. Okay, so now we're going to now we're going to run through the whole data set like so. So now, yeah, we've got tons of data, lots of lines, and we're going to and each line has a time, x, y, and z values. But actually, I think we want to this thing is actually giving us a floating point number. It would be slightly tighter if we make it into an integer. Okay, so now you see the first entry is an integer. Okay, so okay, but now we're going to just change this in a slightly different form. Okay, so we're going to convert it into a NumPy array, and then t0 is going to be okay. So this is giving us the array of times. So we do remember you do so the data we had previously. This kind of first index is sort of the number. So it goes 0, 1, 2. It's up to many thousands. And then the second index, if the second index is 0, that gives us a time. So second index is 1, that gives us the x, etc. So here our t0 is the data colon comma 0, so that's all the times. And we're going to and then because we did the NumPy array, it will have made it float again, so we're going to turn it back into an integer. And then x, y, z 0. Okay, so that's and then we do x, y, z 0. So now this is going to be the array of all the x, y, z things. Okay, so but now we need to, as I said, we need to do a little bit of extra processing. We've got the times normally increase in steps of 4 minutes, which is 240 seconds. You know, we've got our t values are in seconds at the moment, and so they should increase by 240. So let's kind of see that. So we can do. Okay, so do np.diff t0, so that tells us the differences between time steps, and you can see that well, we're seeing a bunch of 240s, and actually the very last one is not 240, it's 180. So you plot all the time differences, and you can see that they're normally here at 240. Occasionally you've got they're different, and then right in the middle, this is kind of close to where the reboost operation appears. We've got the time differences drop down to, I'm not sure if that's exactly 0 or just close to 0, but for some reason, we're not measuring it. Either got a bunch of measurements at the same time, or just separated by a few seconds or something in the middle. So this is going to mess up our signal processing operations. Can't deal with that. We need to clean up our data set. There's a sort of rather common requirement in sort of data science applications. We've got data sets that's somehow noisy, and we need to tidy it up. So what we're going to do is we're going to have an extra block of code in which we're going to just get a data set extracted from the original data set, but with the time steps kind of always being precisely 240 seconds. So this is kind of the number of seconds kind of all the way to the end. And divide by 240. And so this is the okay, so this is the total number of 4-second steps over the whole data set. This actually turns out to be equivalent to 15 days. Okay, so we're going to call this n, right? This is the number of 4-minute steps over the whole time period. And so now we're going to try and so we want our times to be kind of 0 up to n-1, all multiplied by 240. So we're going to build this up as a list. So we're going to start list is okay. We're going to build up a list of times and a list of x, y, z coordinates. And we're just going to start with the time 0 and the initial x, y, z. Okay, and then we're going to build up. Okay, and then we're going to build up our list of times, and the next newest time is just going to be I times 240. And and then we're going to try and find out what our x, y, z position should be at this particular time. Okay, so so we're going to look, do j as np.argmax t0 greater than or equal to I times 240. So what will normally happen is that this time, I times 240 seconds, that will be an entry in our original array of times t0. Okay, and in that case, this j will pick up the relevant point in there, and then we could just set, we can just do x, y, z j is going to be equal to x, x, y, z at I is going to be x, y, z naught at j, right? We're just going to copy the x, y, z position from the x, y, z naught array into the x, y, z array. But sometimes it's going to happen that we don't actually get this this time I times 240 seconds does not actually appear in the T0 data set, in which case we have to do some kind of linear interpolation. So we're going to do this guy here. So S is going to be T0J. Okay, so now what you see, what we're going to hope is going to happen is that this time I times 240 appears in T0. In that case, T0J is going to be equal to I times 240, and then this parameter S is going to be 0. Okay, so again, yeah, so like I say, the normal pattern is going to be that T0J is just equal to I times 240. That will happen if I times 240 appears in the T0 array. In that case, S will be 0, and then what we've got here is S. We're just using XYZ naught J, and that's what we're going to append into the XYZ array. But sometimes it's going to happen that this time I times 240 does not appear in the T0 array. In this case, it works out that by this parameter S is going to be non-zero, and this this thing that we're appending to the XYZ array is going to be somewhere between XYZ naught J and XYZ naught J minus 1. And if you think about it a little bit, this is the correct kind of thing to do, to linearly interpolate to get the expected value of XYZ at I times 240 seconds. If that information is not precisely contained in T0, but we've got some times to a little bit less and a little bit more than T0 than I times 240, then we interpolate between them to get the value of XYZ at that point. Okay, so that's the appropriate way to do this kind of linear interpretation to get this this thing here. Okay, so if we so we just look at what we've got in T. So T is 0, 240, 480, etc. It's just multiples of multiples of 240 seconds. And if we look at XYZ, okay, so that's going to be a list of arrays of length 3, giving XYZ coordinates at particular points in time. Yeah. So we're just going to tidy this up a little bit. So at the moment, T is in seconds, and it's a list. So we're going to convert it to an array, and then we're going to divide it by 60 times 60, so to convert it into hours. And then XYZ, that was a list of arrays. So we're going to convert it into a single array, and then we're going to split it into 3 arrays. So that's the array of X values. That's the array of Y values. And that's the array of Z values. Okay, so yeah, so there's our basic data. So we could try and plot T against X, but yeah, there's just kind of too many points. You just can't really see it. So let's just do maybe for first 1,000 T values and the first 1,000 X values. Okay, so now you can see we've got a kind of fairly regular oscillation, but the amplitude of the oscillation's increasing a bit. Okay, we could let's maybe just do the first 100. So now you can again you can see the oscillation now because we've only got 100 points. You can't actually see too well that the amplitude's increasing, but yeah, but it is. Okay, so there we've got that. Okay, but in order to do these plots, we want to some things are going to change in the plots at those events that we talked about. If you remember, there was these events where the space station gets boosted and one spacecraft undocks and so on. So we're going to we need to take account of the times of those. So here's the times, right? So as I said, the in this file here, it tells us that this thing's happening at day 117, this is happening at day 121, and we had to think a little bit about which days they were once the dates in normal format. But after you think about that, so the first day 1117 is the 26th of April, so that's what it is in this kind of more normal format, and then so the second event was also 26th of April, and the last one was the 30th of April. So there's those, and then we're going to again we want to kind of convert these into kind of hours since the beginning of the. So if you remember on this plot here, this is all kind of about hours since the beginning of the data set. We want to know the times of these events in the same thing. We can do that like that. So again, we use this date time, strip time thing to convert these things into seconds since the beginning of 1970. We subtract this t start that we worked out earlier to get the time from the beginning of the data set, and we divide by 60 times 60 to convert from seconds into hours, and then we'll convert it into a NumPy array. Okay, so now so here's our NumPy array of hours since the beginning of the data set for these various events. Okay, so now we can so now we've got some data and we want to make some plots. Okay, so we're going to okay, but as I said, if we try and do the whole plot, then it's going to be too much. Instead, so we're going to put in a tmin and a tmax, which will be there's the minimum and maximum time that we want to prove, want to show, and but then we want to kind of know the sort of the kind of corresponding index in the original data set. So we so we're going to take this tmin. So that's tmin, that's going to be in hours. We multiply by 15, so that's how many 4-minute blocks we've got, because they're normally, because our measurements are every 4 minutes. So and then so we just do np.floor like that, then we'll get a floating point number which happens to have an integer value, but for later purposes we need to make it be a genuine int, so we do .astype int for that, and so that's the beginning, and then we're going to do the same thing for the end. Okay, so those are the indices within the kind of T array and the XYZ array that we're going to use. And okay, so then we're going to just then we just select out the relevant part of the X, Y, and Z arrays just between index n and index m. Okay, so now we've got Okay, so here's what's happening sort of between 150 hours after the beginning of the data set up to 180 hours after the beginning of the data set. Okay. Okay, and let's actually just label these. Okay, so there we've got display the orbits, and we've got the legend showing which color is which. Okay. But another thing we might want to do is to display the kind of events that appear in this. We had here, and we worked out here. There's various events going on. So let's do a little loop here over the. Okay, so it'll do a loop over the events, and then we have to check whether the event is kind of within the relevant time range that we're interested in. So that's. But these E, we converted them into sort of numbers of hours since the beginning of the data set, which is precisely the same as the kind of Tmin and Tmax scale. So we can just compare with Tmin and Tmax. So if we're in the relevant thing, then we'll just do put in a vertical line. I'll make a black dashed line like so. Oh, that's not what we. Okay, so. Okay, so here we can see that there's two of these events happening here at 158 hours, 173 hours, or something. Can't actually see them too clearly in this picture, although we will be able to see it more clearly on some other plots that we do later. So that's one thing we can do. But actually, we can also do plot kind of x against y or x against z and so on. So let's put that in as well. So we're going to make a so firstly, let's kind of make this plot a bit bigger. So after having done that, though, so now we're going to kind of separately. We're going to do we'll do a plt.show here, and then we're going to start again. So so we can plot x against y. Okay, so we can make 3 subplots like that. Okay, so now you can see you got these kind of ellipses. As x and y varies, it's kind of it's more or less look like straightforward trigonometric functions, which you would expect to give you pure ellipses here. But you can see the ellipses are kind of blurred a bit because the amplitudes and the phases are changing slightly over this period. And if we do a longer time period like this, you see that these ellipses kind of get blurred quite strongly. Okay. Okay, so now we're going to try and work out, do some actual signal analysis and try and get some precise information about the frequency at which these orbits are happening. So one thing we can do is like this. We can do fx px is you do a periodogram. Okay, so we're going to so we put in f as f equals 15. That's because we've got our data is kind of measured in hours, and then we've got 15 samples per hour, one sample every 4 minutes. So that's 15 per hour. So we do fs equals 15 to indicate that. That will give us the correct axes on this plot that we're about to do. And so now we're going to do okay, so what have we got here? We see we've got this graph is a kind of very sharp spike here with 4 times 10 to the 9 there. Okay, so what's this telling us? This is telling us that the variation in x is almost all kind of concentrated at a particular frequency around 2/3. Okay, so around 2/3 of a cycle per hour, which means about one cycle every 1.5 hours, which is 90 minutes. Okay, so you're saying everything is more or less, by far the most important phenomenon is a regular period of around 90 minutes. But we can't really kind of see if there's anything else going on. So it's actually better if we, instead of plotting the px itself, we do we plot its logarithm. Okay, then you can kind of see a bit more what's going on. And we see this kind of business kind of dropping all the way down to kind of minus 50 or something, or below 0. When the log's below 0, which means that the actual power is less than 1, I mean, that's not really showing us anything very interesting. We don't really care. That means that the power is very small, and we don't care exactly how small it is. So it's better if we just do put in np.maximum 0 here, so that just kind of truncates it, so we kind of lose the negative values. They're not very interesting. You see there's some kind of glitchy thing going on at frequency 0. We can probably ignore that. Then we've got this huge spike here, and then there's this kind of extra spike here, which is maybe worth having a bit of a look at. And then everything kind of just drops down towards 0 there. So you should try and actually work out exactly what's the what is the frequency that's going on here. So we can do that using np.argmax. Okay, it's 233. Okay, so but that's okay. So that tells us kind of what number we're looking at. Yeah, this is the 233rd entry in the array. But to get the actual frequency that's involved, we can do fx at that 233. So that's 0.647. So that's the frequency. That's where we're seeing the kind of main effect. Okay, so let's call this so there's our primary frequency. And what's the kind of corresponding period in hours is kind of 1 over the primary frequency. And that's 1.54. It's more conveniently stated in seconds, so it's in minutes. So Okay, so we see 90. It's coming out 92.703, and that is what you'll see on Wikipedia or anything. If you ask about what's the period of rotation of the International Space Station, it's normally stated to be at 93 minutes, and that's what we're seeing in this data here. And I think that will be enough for this initial look at signal processing with the International Space Station.